Organic Chemistry, Exam 4 Material, Part 4. Alkyl halides can be made from alcohols. Taking a look at the reactivity of alcohols, methyl alcohol is the least reactive, and look at the trend as we get more R groups, primary, 2 R groups, secondary, and tertiary. The more R groups, the more reactive the alcohol when we're trying to prepare alkyl halides. The reaction of a tertiary alcohol with HX is fast and effective. So this is best with tertiary alcohols. Adding HCl or HBr gas into an ether solution of a tertiary alcohol gives us a substitution of the OH group with that halogen. The reaction conditions needed aren't just ether. So let's take a look at this. I have HCl gas, ether, and 0 degrees. And again, the same problem we're going to be seeing on and off. For some reason, when I convert to my Mac, I don't get the degree sign, I get the infinity sign. So be sure to change your lecture notes to a degree sign if you happen to have the infinity sign there. So look at this reaction. What's going to happen? Well, under these conditions, OH is going to be substituted for Cl. And this is a tertiary alcohol, so the reaction is going to go well. We see that Cl has substituted for the OH, and we have a minor secondary product of HOH. This H came from the acid, OH came from our alcohol piece. Prepare the following from the appropriate alcohol. So I'm asking you this question kind of backwards. I'm telling you what the product is. It's your job to figure out the right reactant. Go ahead and pause the video, come back, and check your work. 2-chloral 2-methyl propane, so there's my product. I have Cl on carbon number 2, so my OH also needs to be on carbon number 2. Because this is a chloro, I needed to have HCl, ether, and 0 degrees, and I also have my minor secondary product of water. 2-bromo 2,4-dimethyl hexane. My bromo is on carbon number 2. That means my alcohol feature must also be on carbon number 2. Because we're adding bromo, this will be HBr. Again, ether, 0 degrees Celsius, and a minor secondary product of water. Now let's take a look at primary and secondary alcohols. Now they don't react as well as tertiary. In fact, they react very slowly and often rearrange, so we have to find some alternative methods. We want to use some specific reagents to avoid acid and rearrangements of the carbon skeleton. So we're going to use phenyl chloride, and this can convert alcohols to alkyl chlorides. And we use phosphorus tribromide to convert alcohols to alkyl bromides. This could be either a primary or secondary alcohol, so you have one H group here. This is the set of conditions when we use phenyl chloride. We also need to use a pyridine solvent, and we get 2 minor secondary products that you need to keep track of, SO2 and HCl. And again, wherever the OH was, the chloride is going to substitute that spot. If we want to get a bromine on a secondary or primary alcohol, we need to use PBr3 and also ether. And we get our substitution of bromine where the alcohol piece was, and our minor secondary product, H3PO3. On this second reaction here, you can notice I have more oxygens than I started off with. So you need to balance this with coefficients. On our starting alcohol, you need a 3 there. You would need 3 of these compounds here also. Reactions of alkyl halides using the Grignard reagent. On Grignard reactions, we start with a Grignard reagent that acts as a carbon nucleophile towards carbonyl compounds. The preparation of the Grignard reagent is the reaction of the alkyl halide in magnesium in either ether or THF. Now, THF is also an ether, so ether is kind of a generic word, but you can also specifically use THF. Here's our alkyl halide. This is metal in its standard state, so this is literally magnesium metal in its metal form with ether. And what happens is, this is kind of fun, Grignard figured out that the magnesium just kind of scoots its way right in between the carbon that had the halogen, and it's still holding on to that halogen. This reaction can be a halogen of either chloride, bromide, or iodide, and this is what you end up getting. It's known as an organometallic product. Because magnesium is not electronegative, in fact, carbon is more electronegative than magnesium, the electron cloud is going to be pulled towards this carbon. So we now have a delta negative on our carbon, and now we have a basic and nucleophilic carbon. See how the magnesium just kind of gets in there? It's going to be bonded to the carbon here, but it's still holding on to its iodine. It's going to be slightly positively charged. This is my Grignard reagent. Now we can use that to do a whole bunch of reactions. Reactions of Grignard reagents include a conversion from an alkyl halide using the Grignard reagent to an alkane. And this is through protonization. This comes from H3O+. The general reactions here, and this is one from your textbook. I think it's interesting. They used a whole bunch of carbons. Here's your active spot. This is where the reaction's happening. Magnesium and ether. Notice I'm making my Grignard reagent on this step. Magnesium just comes right on in there. And then if we bring in water, what's going to happen is we're going to protonate it. This magnesium and bromide is going to go away, and we're going to protonate this final carbon here, making an alkane. Another use of Grignard reagent is we can go ahead and it can behave as an R- and add to the carbonyl group. I went ahead and numbered the carbons 1, 2, and 3 so you could see where they go, but the R groups could still be the same as each other or different, but I wanted to let you see where everything went. So my initial Grignard reagent, remember we make the Grignard reagent first, and now we're going to use it. So this has R group number 1. My carbonyl group has R group 2 and 3 here. Well, what's going to happen is my magnesium is going to give to this carbon here, it's going to give its R group, so this is R1 here, and now my magnesium is going to be bonded to this oxygen. So this oxygen is no longer double bonded to carbon here as it was here. It's going to now have a bond to magnesium here and the original carbon. Well, what can happen is we can get rid of this magnesium and bromide by bringing in acid and water, and the MgBr goes away and it makes an alcohol. Here's a slide of a lot of different reactions that can happen with the Grignard reagent. You don't need to know all of these. Now, in fact, in this course, we're not going to cover a whole bunch of these. But I wanted you to see the versatility of the Grignard reagent. The Grignard reagent basically puts more carbon on carbon. Continuing on with the organic metallic coupling reactions, so our Grignard reagent was the first organometallic reaction we saw. Let's look at another one. We're starting off with an alkyl halide. We bring in 2 moles of lithium in pentane, and we're going to have bromo replaced with lithium. We also have a minor secondary product of LiBr. Now that we have our organometallic formed, we can use this organometallic and react it with copper iodine, and what we're going to form is known as a Gilman reagent. So Grignard used magnesium in his organometallic reaction, and Gilman uses a combination of both copper and lithium. Let's see what happens. In this case, note that we have 2 moles of our alkyl lithium compound, copper iodine in ether and 0 degrees Celsius. And what's going to happen is our copper is going to grab both of those R groups. That's why we had to have 2 here. We'll have a copper minus hanging out ionically with the lithium plus, and also a minor secondary product of lithium iodine. But it's this piece right here that's your Gilman reagent. Now we have an organometallic ready to react and do more. Continuing on using our organometallic, the Gilman reagent, lithium dialkyl copper reagents react with alkyl halides to give alkanes. And these aren't just alkanes of the original. These are molecules that are bigger, more carbons than we started off with. This is our Gilman reagent. It can react with an alkyl halide, and what's going to happen is we're going to put more carbons on carbon. This has 8, 9, 10. This has 10 carbons, 1 iododecane. And when we take our organometallic, this Gilman reagent, this copper and lithium is going to get out of there, but one of these R groups is now going to attach where this halogen was. Iodine is a great leaving group. So iodine is going to be used quite a bit in these kind of reactions. It's a big bulky molecule. It's not tightly held. In fact, it's very loosely held to this carbon here, so it's a great leaving group. We're going to have ether in 0 degrees Celsius, and where the iodine was, one of these R groups is now going to attach, and we have two more minor secondary products of LiI, and then that second R group is going to grab onto a copper here. Utility of organometallic coupling in synthesis. Coupling of two organometallic molecules produces a larger molecule from smaller molecules. Aryl and vinyl organometallics are also effective. Coupling of lithium dialkyl copper molecules proceeds through trialkyl copper intermediate. In this section here, this is where we have our Gilman reagent, and one of these R groups is going to substitute where the iodine was, so we can see this product here is formed. An overall reaction, we have to first make our Gilman reagent. So we have, this is from a couple slides back, so we're putting this all together. We have two of our R groups with iodine reacting with lithium and pentane. And to finish forming the Gilman reagent, the second step is to bring in our copper iodine. And now we have our Gilman reagent formed. Then we can bring in a different, it doesn't have to be the same as this one here. We can bring in a different alkyl halide in ether. And now we can form, from the coupling of two organometallics, a much larger molecule. Problem: provide the structures for the reactants, intermediates, or products as indicated in the following reactions. Draw the structures in the boxes provided. Go ahead and pause the video, come on back, and check your work. This first reaction is using a Gilman reagent, and this is the alkane we're formed. Notice we started off with 2 carbons, and now we have 3 in our major product here. On the second reaction, I noticed that I cut off my chlorine here when I made this, so this is a Cl. And on the third one, all we did was make our Grignard reagent. We haven't reacted it yet. Oxidation and reduction in organic chemistry. In organic chemistry, we say that oxidation occurs when a carbon or hydrogen that is connected to a carbon atom in a structure is replaced by oxygen, nitrogen, or halogen. It's not defined as the loss of electrons in atoms as in inorganic chemistry. Oxidation is a reaction that results in a loss of electron density at the carbon as more electronegative atoms replace hydrogen or carbon. A reduction is the opposite of oxidation, results in the gain of electron density at carbon with the replacement of an electronegative atom by hydrogen or carbon. Here we can see an example of an oxidation and reduction. An oxidation is breaking of a CH or CC bond to form CO bond, CN bond, or CX bond. In our first reaction here, what's going to happen is we're actually breaking a carbon-hydrogen bond, and it's forming a carbon-chloride bond. Since we have a broken carbon-hydrogen bond and a formed carbon-chloride bond, chloride being more electronegative, this is an example of an oxidation reaction. A reduction is when we form a CH or CC bond and we break the carbon-oxygen, carbon-nitrogen, or carbon-halogen bond. In this case, when we take a Grignard reagent, magnesium and ether, and then we protonate it in a second step, we take carbon that was bonded to chloride, and now we have a hydrogen there. So carbon has more bonds to hydrogen than it had before. This is an example of a reduction reaction. Predict if this is oxidation, reduction, or neither. So really pragmatically, what you're looking for is either more bonds to hydrogen or less bonds to hydrogen, or even more bonds to an electronegative element or not. But it might balance out. So one of these, I'm just going to let you know, is neither. Go ahead and pause the video, come back, and see how you did. This first one's an oxidation because two new bonds formed between carbon and a more electronegative element, in this case, Br. This is a reduction. We have two new bonds formed between carbon and a less electronegative element, in this case, hydrogen. And we also have more bonds to hydrogen. This last example is neither. We both get a new bond to HC and also Br and C, so it evens out. This is neither oxidation nor reduction. Practicing a little more, indicate if the following reactions are oxidation, reduction, or neither. I suggest not just writing if it's oxidation or reduction, write out your reasoning with that. Pause the video, make your prediction, come on back and check your work. The first one's an oxidation. A double bond oxygen is formed and it lost an H. More bonds to oxygen, less bonds to hydrogen. In B, it's neither, because we both have a carbon-nitrogen bond formed, something that's more electronegative. We have a carbon-carbon bond broken, and we added a hydrogen. The third one is reduction. We lost our halogen, and we have more bonds to hydrogen now. Oxidation levels. Functional groups are associated with specific levels. As we go across this chart here, the thing that has the highest oxidation level would be carbonyl. Remember, this is a carbon double bonded to two different oxygens. And then we also have carbon bonded 4 times. It's 4 different chlorides, but it is bonded 4 times to chlorine. So both of these are highly electronegative. And then as we get lower oxidation level, let's go to the worst one on the far end here. I don't want you to miss this CH3. This has absolutely no bonds to anything that's more electronegative. It's a plain old alkane, so this would be the lowest oxidation level. And as we go across this chart here, you'll see that the more bonds we have to something that's more electronegative, the higher oxidation level we get. Your textbook likes to draw carboxylic acid as CO2 with a subscript H. A lot of times you'll see it written as COOH, and then to expand it all the way, it would be C double bonded to an oxygen and then an OH. So I just wanted you to know what that structure looks like. So this first column here, we have no bonds to something more electronegative. Here we have a carbon-carbon double bond, so that gives it a little more oxidation level than not having any double bond, having a single bond. This CH3OH, one bond to something electronegative, same thing with the two beneath it. The next column, we now have a carbon-carbon triple bond, so that would be one more oxidation level up from the double bond. 2 bonds to oxygen, 2 bonds to chlorine, 2 bonds to nitrogen, and then you can see the pattern happening. 3 bonds here and 4 bonds here. These are the functional groups and their oxidation levels. Rank the following compounds in order of increasing oxidation level. Number 1 would be the lowest and 4 the highest. Pause the video, make your prediction, come on back and check your work. What I have as number 1 is this has no electronegative element involved at all. What I have as number 2 happens to have this pi electron here, so this has a carbon-carbon double bond. 3, this has 2 bonds to oxygen, and number 4 has 3 bonds to oxygen. How'd you do?